Your phone will be obsolete in 3 years. The locomotive hauling freight right now may ride on a frame forged before World War II. That sounds insane, until you learn these machines were never built to be replaced. They were built to be rebuilt, stripped down, re-engined, upgraded decade after decade on the same over-engineered steel. The reason railroads still depend on them comes down to something modern manufacturers abandoned long ago. A locomotive frame from the 1940s is not just a piece of steel, it is the backbone of a machine built to outlast its designers. While most products today are engineered for a short, predictable life, these frames were forged from carbon steels that rival the strength of modern ASTM A572 grade 50, with yield strengths ranging from 36,000 to 50,000 pounds per square inch. Manufacturers like EMD, Alco, and Baldwin specified main side sills up to 1.75 inches thick, often reinforced with welded ribs and gusset plates. The result was a structure designed to handle not just the daily pounding of freight service, but also the unknowns of war, weather, and time. Blueprints from the era lay out safety factors of 2.5 to 3, meaning the steel was expected to withstand 2 or 3 times the maximum load it would ever see in service. This was not accidental. During World War II, government orders demanded even higher margins, driving the use of heavy gauge plate and conservative welds. The extra metal was not just insurance, it was a deliberate buffer against fatigue, cracks, and the relentless stress of millions of miles. Metallurgical studies decades later confirm that these frames still meet or exceed their original specifications. Hardness tests on a 1948 EMD GP9 frame, for example, reveal a tensile strength that matches the best modern structural steels. For railroads, this overbuilt geometry is more than nostalgia. It is a physical asset that can be stripped, inspected, and rebuilt again and again. The steel does not care how many engines or control systems come and go. It was designed to endure, and that is exactly what it does. A locomotive frame built with a 2.5 to 3.0 safety margin is more than just a tough piece of metal. It is a platform designed to outlive its original purpose. That oversized buffer against stress and fatigue means the steel does not just survive decades of pounding, it shrugs it off, accumulating millions of cycles without reaching its breaking point. In engineering terms, this is the difference between a product that is built to last a warranty period and one that is built to be reborn over and over. This mindset transforms the locomotive frame into a kind of industrial foundation. Engines, traction motors, and control systems can be swapped out as technology changes or regulations tighten, but the frame remains, ready to host each new generation of components. The result is a machine that evolves, not just endures. Fatigue cracks or worn mounting points are not the end. They are an expected part of the maintenance cycle, fixed by welding, bolting, or reinforcement, all without compromising the core structure. Decades of metallurgical testing back up this philosophy. Even after half a century, frames from the 1940s and the 50s retain their original strength, with hardness and tensile values that rival modern standards. For railroads, this means the frame is not a relic, it is a reusable asset, a base for upgrades, and a shield against the high cost of new equipment. In an industry where a new locomotive can cost upwards of $4 million, the ability to rebuild on a proven frame is not just practical, it is essential. The old steel, overbuilt and understressed, becomes the anchor for generations of reliable service. Inside the locomotive shop, a work order lands on the foreman's desk. Engine replacement, EMD GP9, frame number 1527. The process begins before sunrise. Crews disconnect cooling lines, air hoses, and electrical harnesses, labeling each for reassembly. The prime mover, a 16-cylinder diesel weighing over 30,000 pounds, must be lifted clear. By noon, the old engine hangs from a hydraulic crane, its mounting pads exposed for the first time in decades. The shop clock tracks every step, and the foreman's log records the start and finish down to the minute. With the engine bay open, teams inspect the frame and mounting points for fatigue cracks or corrosion. Any flaws are ground out and welded, often by the same hands that will guide the new engine into place. A replacement prime mover rebuilt to modern emission standards arrives on a custom trolley. It is aligned by laser, bolted in place, and connected to the generator and control harnesses. The shop standard is clear: no shortcuts, no guesswork. The entire swap, from the first wrench turn to the final test run, averages 48 to 72 hours. It takes about 250 person-hours, spread across electricians, welders, and machinists. The shop foreman's notes from a 1992 rebuild spell it out. Engine out by 8:10 a.m., new unit seated by noon the next day, test fired by 2:30 p.m. 0 defects. This is not a side project. It is a practiced routine, repeated dozens of times per year. Each swap extends the locomotive's useful life by a decade or more, at a fraction of the cost of new equipment. The modular design makes it possible, but it is the discipline of the shop crew that makes it real. Modernizing an old locomotive goes far beyond swapping engines. Electronic fuel injection modules now take the place of mechanical governors, allowing a frame from the 1950s to meet 21st century emissions rules with pinpoint fuel delivery. EFI upgrades alone can boost fuel efficiency by 3 to 5% and help railroads comply with EPA Tier 2 or Tier 3 standards. It is a leap in precision that would have sounded like science fiction to the original builders, yet it bolts directly onto a frame forged when Eisenhower was president. Control systems, once a maze of relays and analog dials, are replaced with microprocessor-based units. These digital brains monitor temperatures, pressures, and voltages hundreds of times per second, catching faults before they become failures. The cab that once echoed with the clatter of mechanical switches now hums quietly under the direction of electronic modules, some designed to interface with satellite tracking and remote diagnostics. The result is a more digital operating environment. Braking, too, has evolved. Electronically controlled pneumatic brake packages are now fitted to older units, reducing the delay between engineer command and brake application across a mile-long train. This upgrade is not just about smoother stops, it is about safety compliance. ECP systems align aging locomotives with the latest federal safety regulations, all without replacing the underlying steel. Each retrofit is a calculated investment. Installing EFI and ECP systems typically adds $25,000 to $45,000 to a rebuild bill, and it is still a fraction of the millions required for a new locomotive. The result is a machine that looks ageless on the outside but carries decades of technological evolution within. For railroads, this approach is not about nostalgia. It is about extracting every ounce of value from proven assets, sidestepping the financial shock of new purchases, and keeping reliable power on the rails for another generation. The financial gap between rebuilding an old locomotive and buying new is nothing short of staggering. A brand new diesel-electric road locomotive today commands a price tag between $3 and $4 million. By contrast, a full-scale rebuild, complete with a modern engine, upgraded traction motors, and digital controls, usually lands between $800,000 and $1.2 million. That's less than a third of the cost, sometimes even a quarter, for a machine that can deliver another decade or more of reliable service. For railroads operating on tight margins, this difference isn't just appealing, it's survival math. The numbers are clear. For every new locomotive purchased, a railroad could instead rebuild 3 or even 4 proven workhorses. The capital saved can be redirected to track upgrades, safety systems, or simply keeping the lights on during lean years. In an industry where every dollar counts, the price difference alone makes the case. Rebuilt locomotives find their true calling in jobs where reliability and cost control matter most. Yard switching and short-haul freight are prime examples, tasks that demand constant starts, stops, and low-speed maneuvering, rather than high horsepower or the latest technology. For these roles, the proven frames and updated systems of an older unit are not a compromise, but an advantage. Accelerated depreciation schedules let railroads recover investment quickly, while the lower upfront cost of a rebuild protects precious capital. The result is a machine perfectly matched to its assignment: tough, dependable, and able to shoulder the daily grind without the financial burden of brand new equipment. For many operators, it is not just about saving money, it is about getting the right tool for the job every single day. In an age obsessed with the new, railroads quietly profit from machines built for a future their inventors could barely imagine. Every rebuilt frame is proof. Durability and adaptability outlast trends, and they outpace costs. The real innovation isn't replacement, it's relentless survival. What endures in the end wins.